So in the morning session, we have started discussing about the gas lasers. So we discussed the helium neon laser. So that is atomic laser where helium atoms and neon atoms are placed in a gas chamber. So with the percentage of 90% of helium and 10% of neon. So this mixture will allow you to having a lasing action because of the energy levels. Having a population inversion will be created in this neon energy levels. Okay, because see, these neon energy levels are not directly excited, so you excite the helium atoms. So these helium atoms will collide the neon atoms. They transfer the energy or the electrons to neon. So now these states are metastable states having lifetimes of hundreds of nanoseconds. So then you have a population inversion between your singlet states of 5s and 4s and 3s to your 4p and 3p states. So you have a transition takes place in this way, so that you have a lasing action at different wavelengths. So these are all possible wavelengths. So with the most prominent lasing action, generally helium neon laser is well known for 632.8 nanometers. So that is a transition from this state to this state. Okay, so that's all about the helium neon laser. So then we come to know about the ion lasers. So ion lasers are also a gas lasers. So where argon ions having a lasing action. So we know that your argon, this is the energy level. Now if you see, this is the argon ground state. So where your argon atom in the ground state, but the ground state level for argon ion will be this state. So that means this is the exact state of the argon ion. So where it is a stable state. So now you maintain the either the temperature, or you always create argon ions in your gas medium. So then this state is a ground state. Then you have a transition, your electronic transitions to higher energy levels. So these are higher energy levels, like you can see these are the S off and P D orbitals. So now you have higher excitations here. So once you pump these states, now you have a lasing. These are all energy bands, you can say. So there are multiple energy levels. So now from these states to this state, you have a transition. So these are the laser transitions. So now you can get actually in the visible wavelengths. This argon ion laser gives multiple wavelengths in the visible range. So these are a few of them, like more prominent wavelengths. Like in principle, most of the argon ion lasers are working in the 14.5 nanometers. And so this argon ion laser can have a tunability to get the different wavelengths in the visible range. So you will get around 488, 457. There are other couple of in the red color. So you can have, there are suitable energy levels to get the lasing action in the visible range. Okay, so this is the typical diagram, the schematic of your argon ion laser. As you see, these are the two N mirrors. Okay, so then you have a gas chamber. So your gas chamber, this is your gas inlets. So you have a gas inlet and gas outlet, and the other side you have a cooling. Either you do a water cooling or air cooling. So this cooling unit to reduce the heat at the system. Okay, so now you have a discharge tube, so that you have electrons going through in this direction. So that you have created a potential so that the electron gains the energy. So this way your lasing action takes place. To that means you excite the transitions to higher states. From there you have the spontaneous emission, and this spontaneous emission trigger the stimulated emission in this laser cavity. So this is the laser system, one of the laser system. You can see how this argon ion laser. Okay, so this is the unit, the argon ion laser unit. So this is compatible, which is a gas laser and gives a good amount of energy for to use. Okay, so this is all about argon ion lasers. And the most famous laser in the gaseous state is apart from the helium neon laser, there is a CO2 laser. So the CO2 gas laser, the laser active medium is gaseous carbon dioxide. So in this you have a typical mixture of carbon dioxide, nitrogen gas and helium atoms. So now the concentration of these gases in the form of 1:1:8. So now you have 1% of carbon and 1% of nitrogen, you have 8% of your helium atoms. So that means that you are almost close to 82% of helium ions or helium atoms, and you have 13.5% of nitrogen, and CO2 is 4.5% in your gas chamber. So that is general common mixture how the people use to produce a CO2 laser. So now the gas chamber will be like this. So you have an end mirror, so where it is a highly reflecting mirror, and the other side is you have a partially reflecting mirror. So these are your gas inlets. So you apply a gas flow, then you create a potential, you have a high voltage supply. Okay, so these are the electrodes will mount on this tube. So this is how you send a gas in and you have gas outlet, so that you maintain the same concentration. As you mentioned, the pressure has to be maintained to create a lasing action in CO2. So now this is the typical energy level. So I'm not talking about helium ions, because helium ions will transfer energy to nitrogen. So also you have a ground state, you can excite to nitrogen atoms. So these nitrogen atoms will collide with the CO2 molecules. Okay, your nitrogen atoms, the excited nitrogen atoms collide with your CO2 molecules. So now your CO2 molecule has a different vibrational states, so which will match with the energy levels of your nitrogen energy levels. So now for example, if you see your CO2, the mode which is called asymmetric mode. So now you see your carbon atom and either sides you have a oxygen. So now these are a stretching mode. So this stretching in the same direction. So now the oxygen atoms, for example, in principle, now you have a carbon, you have oxygen, and you have oxygen. So now the stretching mode, your oxygen is stretching in this direction, and also your oxygen is stretching in this direction. What happens? This oxygen come closer to this carbon, and this oxygen will go far from the carbon. So that is one of the stretching mode or vibrational mode of the carbon dioxide. That energy level will match with the excited nitrogen gas. So now there is a collision and you have a energy transfer to this state. So that means now this state is populated. So once that asymmetric stretching mode is populated, now what happens? So you have a transition to other modes where you have a symmetric stretch. So this is the energy level. This is the energy level because of the asymmetric stretching. So this energy level is because of the asymmetric stretching. There is one more energy level exists here. This is due to the symmetric stretch of your carbon dioxide, so that your both oxygen atoms will stretch towards the carbon. So that is your stretching mode. This is called a symmetric stretching mode of your carbon dioxide. So that creates energy level here. So and then there is one more energy level or energy kind of band for the acid bending stretch. So now you not only this stretching in axial direction, so out of the axial direction you have a stretching your carbon and oxygen. This oxygen will bend towards this perpendicular to your axial direction. So this is your axial direction, this is perpendicular to axial direction, you have a stretching, that is called bending. Okay, so now you have a bending will be energy levels in this lower excited state. Now you see, once you populate asymmetric stretch energy level, so this energy will be relaxed, that means it will decay to this mode, okay, or this can be relaxed to this mode. By doing the relaxation process, Okay, the transition gives you the wavelengths around 10.6 micrometer and 9.6 micrometers. So that's what the transition happens due to the energy level at this asymmetric stretch mode is not enough lifetime, like it has like act as a metastable state. So then you have a relaxation to a symmetric stretch energy level or a bending stretch energy level. So while relaxing to these states, you have a photon emission. So that is at around 10.6 micrometer and 9.6 micrometer. So now once they come to these states, lower laser action energy levels, so these energies will be like non-radiative decay to the ground state. Okay, so this decay will be generally fast non-radiative process. So this is the how your lasing action taking place in a CO2 gas laser. So your helium atoms will collide to the nitrogen atoms, so that by collision it gives the energy to the nitrogen, and also simultaneously you excite the nitrogen atoms depending on the matching of the energy levels. So then once you have excited nitrogen atoms, they will collide with the CO2 molecules. So when they have a collision, they will immediately transfer those excited energy levels to CO2. Then CO2 is a excited state at this mode. So that is a asymmetric stretch mode. So then you have relaxations accordingly. So this is about the CO2 gas laser. So the emission wavelengths around 10.6 micrometer and 9.6 micrometer. So the laser power, you will get a enormous laser output. So that is in the order of 10 power 6 watts. So you will get a high power laser. So that is your megawatt, 10 power 6 watt in SCW operation. Okay, so in principle, this kind of a laser wavelengths can be penetrate easily up to 10 to 30 microns into the tissues. So this can be used in a medical purpose, and also you heard about the pulsar laser deposition. In many of the material scientists generally use this technique called pulsar laser deposition. So in that case, you need to use a high power lasers. So where generally the CO2 laser is a better suit to have a pulsar laser deposition technique. So they use to coat any material using like you want to coat a silver ions or you want to coat any metals onto your substrate. So you use a pulsar laser deposition. So you come with a high energy. So you rip off the atoms from your metal, then you deposit onto the substrate. So this kind of a method, generally the CO2 laser is a better suit because having a high power. Okay, so if you heard about any pulsar laser deposition, so where generally CO2 laser is a main source to do the process. Okay, so now we move on to Excimer laser. So Excimer laser is one type of a chemical laser. So it's a part of a gas lasers. So Excimer lasers, Excimer is nothing but a short-lived excited dimer. So dimer means a two ions. Okay, it's bound ions that you call Excimer. So in general, it is a short-lived dimer. So either it is a same kind of materials or it's a different atoms. If it is the same, then it's kind of a homodimer. Generally, you call dimer. And if it is a different, it's called a heterodimer. So that means the Excimer is a bound excited ions. Okay, that is you call Excimer. Okay, so that means either two atoms or same atoms are in excited state are bound together, that is called Excimer, or two different atoms having a bound state at the excited state, that is also called a dimer. So that is about the excited dimer is called Excimer. Okay, so in this case the formation of molecules is possible only if such atoms are in a electronic excited states. So these dimers will be formed at the excited state, that is you call Excimer. Okay, so now often these Excimers are composed of two atoms or two molecules. If they are in the ground state, they don't have any bonding. When they are excited, they have a bonding. So that is the basic understanding of the Excimer. So in general, the lifetime of Excimer is very short. It's in general of order of nanoseconds. So binding energy or a large number of excited atoms form a Rydberg matter clusters, where then you have a large number of these kind of Excimers, okay, making as a clusters. Then you have expected to have a lifetimes can be increased to up to seconds. So now this is the typical schematic of Excimer laser. So these two are our end mirrors. This is 100% or close to 100% highly reflecting mirror, and this is your partially reflecting mirror. Now you have a chamber created to having your gas inlets, okay. So now you combine two different gas molecules, or for example in this case you send a CaF2, so Ca one direction and F2 in one direction, okay. So now this gas flows at the entrance or at the exit of the gas outlets. You have a formation of the Excimers. So now the chemical reaction will take place at these gaps, okay. At these gaps you have a chemical reaction, then you have a continuous emission takes place, the spontaneous emission. So once you have a spontaneous emission, then these gas molecules are available here, the Excimers, then you stimulate them because of your feedback. When you have spontaneous emission, the spontaneous emission feedback come into again to the cavity. So during the round trip, they will interact with the excited your dimers. So then you have stimulate emission. So that is the basic principle happens in Excimer lasers. So this kind of a arrangement gives you more efficient chemical reactions. See, if you send only one inlet, the uniformity of reactions will be different, so your lasing action will be difficult to achieve. So in this method you create different outlets of your gas molecules so that you have a uniform interactions, the chemical reactions will take place. So this is the optimized method to having a Excimer laser, okay. So in principle the Excimer lasers are very famous for getting a UV wavelengths. So now if you see from the Excimer wavelengths range from 126 nanometers to 351 nanometers. Now if you see, these are a deep UV light. So now in the COVID situation we are required to have UV lasers so that you can disinfect whatever the rooms or the vegetables you want to disinfect, any like these kind of a COVID viruses. So in general these wavelengths will kill the virus in principle. So most of the virus cannot sustain in the UV radiation. So that is the reason people generally to disinfect their office rooms or the laboratories or the medical centers, hospitals, they are going to use UV lights, okay. So these kind of lasers can also be utilized to create or to disinfect the rooms or the hospitals, okay. The major advantage because they have very good UV emission and they give very high powers. It's, you can see 200 watts. So not only disinfect the things, if for example any N95 mask you want to reuse, so you can actually make a device so that like a device which all the N95 mask goes through this your lasing box. You create some lasing box, so this N95 mask going through like in the rail, so this UV radiation will incident in all directions, that the radiation will kill all the virus. So this method is more efficient because you will almost 99 to 100% you will kill the virus and with a very little time. So because these are high power lasers, with no time you will disinfect 100%. So it's like you can use, looks like a new, okay, because no virus, then you can call as a new N95 mask. Okay, so that is where more advantage of these UV lasers in these pandemic situations. And not only that, these Excimer lasers have many other applications in the medical and industrial applications. So for example, you want to do any fabrication of the devices, generally people use lithographic techniques. So optical lithography technique, generally you require to use a UV light. Okay, so to want, see, because UV light having few nanometers, so you want to make a structure using, because you can have a spot size of 120 nanometers if you use Excimer lasers. If you use a semiconductor lasers, roughly you have 1 micron spot size. So you cannot make any device using in a nanometer scales, because your spot size limits to microns using semiconductor lasers. For example, in this case, you want to make any electrodes or any nanometric devices, you need to use shorter wavelengths. So there, people use generally these UV lasers to do optical lithographic techniques. Okay, so these are the major advantage of the Excimer lasers. So though the efficiency percentage is low, but typical output powers in the order of 200 watts or more, depending upon the number of pumping units. Okay, so it will be pulsed operation possible. So if you want not only continuous, the pulsed also will be possible. So because the system generally use water cooling, because high power lasers you require to cool water cooling. So and partially it's hazard gases will these come out of the chambers. So these are things can be taken care when you work with these Excimer lasers. So now if you see the energy levels of your Excimer lasers, so now for example, you take the example of krypton and fluorine gas. Now if you see, these are all neutral atoms when they are in the ground state. So this plot is energy versus distance between atoms. Okay, so now this is the ground state energy when your krypton atoms and the fluorine atoms in your chamber. So now when they excited, it creates a krypton star. That means you have a ions there. So you have krypton ions and the fluorine ions. So now they are bound. So these ions in a bound state. So you have a krypton F whole star. That means this is an excited state. Okay, in the excited state they are bound together. So now when they are bound together, now you see this green color indicates these are the atoms are excited. So this is the states are filled because of your Excimers. So now what happens when they come down, they release the photons. Okay, so now the tunability comes from, you see, so this is the tunable wavelengths from here to here. So now in this case, now this is your energy. So this is the tunable range you will get using your Excimer laser. Okay, so however you pump more, so that you can have a more Excimers, so that you can create a broad wavelength range. Okay, so that's depending upon the so you can create more broad wavelengths depending upon how you pump to higher energy levels. Okay, so this is about your Excimer laser. So now there are many other atoms or the molecules can be used into as a Excimer laser. For example, argon fluoride or krypton fluoride or krypton chloride, xenon bromide, xenon chloride, xenon fluoride. These all forms a Excimers. Okay, so the wavelength range you can see. So as I mentioned previously, there are other argon also. So if you have these are all different atoms, like not the same atoms. If you want the same atoms, you can have argon. So argon Excimers. Okay, so that is Er2. So you can get argon Excimer. So these wavelengths will be much shorter, so that can gives you even shorter wavelengths. Okay, so this is all about the Excimer lasers. So this having many advantages. You want to do any people generally use for medical purpose also these Excimer lasers, where you want to damage certain tissues which are not required, or these tissues are not harming the other cells, so then they want to kill those tissues. Simply they will excite with the some power of the Excimer lasers. Or in principle there are different usage of Excimer lasers and also CO2 lasers. In principle, in medical purposes, mostly we generally use IR wavelengths. Okay, so because IR wavelengths, as I mentioned in our previous classes, these IR wavelengths which are much suitable to human tissues, because human tissues are mostly composed of 70% of water, where water has very good absorption in the IR region. So that means for any medical purposes, generally IR wavelengths are much suitable for the medical purposes. Okay, but to do any surgeries, any related surgeries, generally these IR wavelengths are very much suitable. Okay, so with that, so we will conclude the different types of lasers. So now you got a very good exposure of wide variety of lasers available in our current technologies. So from solid state lasers to our gas lasers, including our chemical lasers, Excimer lasers, and different dye lasers.